A development team spends 4 months building a machine learning model that predicts customer churn with impressive accuracy. They choose their framework quickly. PyTorch felt right, and they moved fast. At month 5, they tried to deploy the model to production. There is no pipeline to feed it live data. There's no feature store to ensure that the features at inference time match the features at training time. There is no monitoring to detect that the model started degrading. There is no registry tracking to which version is running where. The model works, the stack does not. They are 4 months into building one layer of a 7-layer system without a blueprint for the other 6. This article is that blueprint. This is DIY Machine Learning, the Stack in Plain Language, ML Part 43. Before you pick up a tool or write a line of code, you need to know what you're actually building and in what order pieces go together. Part 1. Why the stack matters before the tools do. Every article in this series has referenced stack layers by name. Data pipelines, Part 3. Feature stores from Part 4. Model registries from Part 5. Monitoring from Part 6. The semantic layers from Parts 14 through 24. Explainability from Part 32. Those references assumed you understood where each layer sits relative to the others. This article makes that relationship explicit before the next 3 articles put named tools in each layer and ask you to choose between them. The stack is not a technology preference, it is an operational requirement. A machine learning system without a data pipeline starves. A model without feature store produces training serving skew that degrades accuracy invisibly. A deployment without monitoring runs blind until business metrics reveal damage that's been accumulating for months. Skipping layers does not simplify the system. It moves the failure to a place where it's harder to detect and more expensive to fix. Part 2. The 7 layers. The data layer is where everything begins. Raw data arrives from operational systems, sensors, logs, documents, and external feeds. The data layer ingests, validates, and stores it in forms that downstream processing can consume reliably. Without clean, consistent, well-governed data, nothing above this layer works as designed. The tools that live here are pipeline orchestrators and data quality frameworks. The languages that run here are primarily Python with SQL for transformation logic. The feature layer sits above raw data and below the model. It transforms raw data into the numerical representation that machine learning models can learn from. A timestamp becomes time of day and day of week features. A customer record becomes a set of behavioral metrics circulating over rolling windows. The feature store is the infrastructure that ensures the features computed at training time are identical to the features computed at inference time. That consistency is what prevents silent accuracy degradation that kills production models. The training layer is where most practitioners spend most of their time and where most of the visible tooling lives. Frameworks like PyTorch and TensorFlow define how models are constructed and optimized. Experiment tracking tools record what was tried, what hyperparameters were used, and what results each experiment produced. Without experiment tracking, model development becomes archaeology. You know what the current model does, but not what you tried to get there or why you made the decisions you made. The registry layer is the version control system for trained models. Every model that passes validation gets registered with its training metadata, performance metrics, and lineage information before it is eligible for deployment. The registry is what allows a team to answer the questions that regulators and auditors ask most often. Which version of the model was running at a specific moment and what data produced it? The deployment layer takes registered models and serves them as prediction endpoints that operational systems can query. This layer manages the infrastructure that runs inference, handles load, routes traffic between model versions during staged rollouts, and executes rollback when a new version underperforms. Edge deployment, which we examined in Part 26, is a deployment layer decision about where inference physically executes, not a separate stack. The monitoring layer watches everything above and below it continuously. Model performance monitoring detects when prediction accuracy degrades. Data drift monitoring detects when incoming features diverge from training distributions. Infrastructure monitoring detects when deployment systems are failing to serve predictions reliably. Without this layer, the stack operates blind. Problems accumulate invisibly until they surface as business failures rather than system alerts. The semantic layer is what parts 14 through 24 built in detail. It sits across the full stack rather than occupying a single position within it. Ontologies define what features mean formally. Knowledge graphs provide grounded context for model inputs and outputs. Provenance tracking makes every assertion in the system reconstructible. In low-stakes commercial deployments, this layer is optional. In regulated domains where predictions drive consequential decisions, it is the layer that determines whether the system can be audited, defended, and trusted over time. Part 3. How the layers connect. Data flows up, governance flows down, failures propagate in both directions. A data quality problem in the data layer produces corrupted features in the feature layer, which trains a model on bad inputs in the training layer, which registers a flawed model in the registry layer, which deploys incorrect predictions in the deployment layer, which monitoring detects weeks later when accuracy metrics diverge from expectations. The failure originated at layer 1 and surfaced at layer 6. Without instrumentation at every layer, tracking it back to the source requires forensic investigation rather than operational monitoring. Understanding this propagation logic is what separates practitioners who debug production systems efficiently from practitioners who spend weeks chasing symptoms without finding causes. The stack is not 7 independent components. It's one system where every layer's output is the next layer's input. Part 4. Why this matters. The next 3 articles put named tools in each layer and ask you to make choices between them. Those choices are only meaningful if you understand what job each layer is doing and what happens when a layer is missing or poorly implemented. A framework choice made without understanding the feature layer it depends on and the registry layer it feeds into is not an architectural decision. It's a preference. The blueprint is the stack. The tools are how you build it, in that order. Next, the languages and frameworks that actually matter, why Python dominates, where Rust is winning, and what the abstraction layer that most practitioners touch first is actually doing underneath.